Hello and welcome to Algebra 2 Lesson 57. In this video, we're going to learn about adding and subtracting radical expressions. So again, most of this chapter where we're talking about radicals is nothing more than a review from Algebra 1. But again, it's something we want to have a refresher on before we move into anything more challenging. So we're going to start by talking about this topic of adding and subtracting radical expressions. So we have here that we add and subtract radical expressions using the distributive property. So this is something similar to when we combined like terms. So for example, if we had something like, let's say 2x minus 5x, what would we do? Well, we would work with the coefficients. We would say 2 minus 5 is negative 3, and then times that common variable, which is x. Now we had some conditions with this. We couldn't say have 2x squared minus 5x and combine those, because those are not like terms, right? So we can't combine them. But if we had something like 2x squared minus 5x squared, then we could combine them. It's got to be the same variable, which in this case it's x and x. It's got to be raised to the same power. This is x squared, this is x squared. So when that occurs, the variable just stays the same. So you'd have x squared, and then you just work with the coefficients. 2 minus 5 is negative 3. So it did the same thing for this and then for this. Now, I'm going to apply that same logic up here. If I have 2 times square root of 7 minus 5 times square root of 7, the square root of 7 part is just going to stay the same. It's the same index, right? A square root has an index of 2, and it has the same radicand. The radicand is 7 in each case, so that just stays the same. Then we just work with what's multiplying the radicals. So 2 is multiplying the square root of 7. 5 is multiplying the square root of 7. So we just do 2 minus 5, which gives us negative 3. So you'd end up with negative 3 times the square root of 7. Another way to kind of look at this, if you wanted a more kind of technical approach to it, you could factor out the square root of 7. So I could say, let me factor out the square root of 7 from each. So I'd have the square root of 7 out in front. And what would be left inside? Well, you'd have this 2 here, then minus, you'd have this 5 here. And then 2 minus 5 is negative 3, and it's multiplying this square root of 7. So this is kind of the more technical approach, probably what you'll see in a textbook. But really all you need to do, as long as the index is the same and the radicand is the same, all you really need to do is work with the numbers that are multiplying that common radical. Again, in this case, it's just 2 minus 5, which gives us negative 3. And we multiply by that common radical, which is square root of 7. All right, let's take a look at another one. So let's say we run across negative 9 times square root of 15 plus 11 times square root of 15. Again, I've got the same index. It's a square root in each case. And I've got the same radicand. I've got a 15 and I've got a 15. So this part is going to stay unchanged. We don't need to do anything with this. We just work with the numbers out in front. So it would be negative 9 plus 11. That would give us 2. And then times that common radical, the square root of 15. Now, as I alluded to, for this to work, we've got to have like radicals. Like radicals have the same index and the same radicand. Now, again, we talked about something similar to this when we were working with polynomials. Remember, we had like terms, same variable raised to the same power. Well, for like radicals, it's the same index with the same radicand. So let's say we see something like this. 4 times square root of 5 plus 8 times square root of 7. Can I do the same technique to simplify here? No, I cannot. I have a square root in each case, so the index is the same. But my radicand here is a 5. My radicand here is a 7. So these are not like radicals, right? So not like radicals here. And it's the same thing as when we saw something like, 4x squared plus 5x cubed. Those are not like terms, so we can't do anything to simplify there. All right, here's another example. So we have negative 3 times the cube root of 7 minus 2 times the fourth root of 7. So in this case, the radicand is the same. So you've got a 7 here and a 7 here, but the indexes are different. This is a 3, right, is a cube root. This is a fourth root. So these are not like radicals. So these are not like radicals. And again, this is the same thing as when we came across non-like terms when we're working with polynomials. So we're not going to simplify this any further than that. All right, let's look at some problems where we can do some simplifying. And we'll come across some things where we have to simplify before we can do addition or subtraction. So we have 7 times the square root of 7 plus 8 times the square root of 7. So again, all I need to do is look at the numbers that are multiplying the radicals. So we have 7 plus 8, that's 15, times that common radical, that's the square root of 7. All right, what about negative 8 times the square root of 10 plus 5 times the square root of 10? Again, all I'm looking at is negative 8 and 5. So negative 8 plus 5 is negative 3, and then times the square root of 10. All right, now we have 2 times the square root of 24 minus 8 times the square root of 24. So 2 minus 8 would give me negative 6, and then times the square root of 24. Now, you don't want to report your answer in this format because why? The reason is if you look at the square root of 24, this is not simplified. We know that if we factored 24, we could get a perfect square from 4, right? 24 you could make as 4 times 6. 4 is a perfect square. So we want to simplify this. So let's make this negative 6 times square root of 4 times square root of 6. This would give us negative 6 times. The square root of 4 is 2. So I could replace that with a 2. Negative 6 times 2 would give me negative 12, and then times the square root of 6. Now this is simplified because the square root of 6, I can't do anything else with that. 6 factors into 3 times 2. No perfect squares in there, so we're basically good to go. All right, for the next one, we have 2 times the square root of 20 minus 3 times the square root of 5 plus 2 times the square root of 5. So you might look at this and say, well, you've got the same index in each case, but I have a 5 as a radicand here, and a 5 as a radicand here, but a 20 as the radicand here. So I can't combine this with any of these. Before you do that, make sure that you factor things. Because if I look at 20, we know it's what? It's 5 times 4. 4 is a perfect square, so that can come out. So really what I can do is I can say this is 2 times the square root of 5 times the square root of 4 minus 3 times the square root of 5 plus 2 times the square root of 5. This is equal to, we know that the square root of 4 is 2. So if this is 2, you'd have 2 times 2, which is 4, times the square root of 5, minus 3 times the square root of 5, plus 2 times the square root of 5. Now that we've simplified, these are all like radicals, so I can just work with the numbers out in front. So in other words, I would say 4 minus 3 is 1, 1 plus 2 is 3. So this would be 3 times that common radical, which is the square root of 5. All right, what about something like this? We have 2 times the square root of 6 minus 3 times the square root of 5 minus 3 times the square root of 45. Now, square root of 6 I can't simplify any further. Square root of 5 I can't simplify any further. But square root of 45, we can do something with that. For the square root of 45, 45 is 9 times 5. 9 is a perfect square. So what I can do, we can write 2 times the square root of 6 minus 3 times the square root of 5 minus 3 times the square root of 9 times the square root of 5. The square root of 9 is 3. So you basically have 3 times 3, which is 9. So let's rewrite this as 2 times the square root of 6 minus 3 times the square root of 5, then minus, we said 3 times 3 would give us 9 times the square root of 5. Although I don't have like radicals everywhere, I can combine these, right? These are like radicals. So what we can say is we'd have 2 times the square root of 6, negative 3 times the square root of 5 minus 9 times the square root of 5. You just take negative 3 and subtract away 9. That would give us negative 12. And then it's times that common radical, which is the square root of 5. So we end up with 2 times the square root of 6 minus 12 times the square root of 5. All right, let's take a look at another one. So we have 2 times the square root of 20 minus the square root of 45 plus 3 times the square root of 54. So I can simplify this. This is what? 5 times 4. We can simplify this. This is 5 times 9. And we can simplify this. This is 6 times 9. And so there's a perfect square as a factor of each of these. So let's go ahead and simplify. So we would have 2 times the square root of 5 times the square root of 4. minus the square root of 5 times the square root of 9 plus 3 times the square root of 6 times the square root of 9. So we know that this is 2. This is 2. We know that this is 3. Right? This is 3. And we know again that this right here is 3. So what do we get? You'd have 2 times 2, which is 4, times the square root of 5, minus, you'd have 3 times the square root of 5, plus, you'd have 3 times 3, which is 9, times the square root of 6. So although we can't combine everything, we can perform this operation here. So we're going to do 4 minus 3, which would give us 1. Now, if 1 is in front, I don't need to write it. I could put 1 times the square root of 5, or I could just put square root of 5, right? 1 times anything is just itself. Then plus, we're going to have 9 times the square root of 6. Now, I can't simplify this any further. These are not like radicals, so this is just my answer. All right, so let's take a look now at 3 times the cube root of 24 minus 3 times the cube root of 54 minus 2 times the cube root of 16. So now we're working with cube roots. So you think about 24, you're looking for a factor that would be a perfect cube, right? A number that when multiplied by itself 3 times gives you that number back. So when I think about 24, are there any factors that would be a perfect cube? Well, yeah, 8 would be, right? 8 is 2 cubed. So 8 times 3, 54. Let's think about that. 54 has 27, right? So 54 is 27 times 2. And 27 is what? It's 3 cubed. 3 times 3 is 9. 9 times 3 is 27. And 16 is what? It's 8 times 2. 8 is a perfect cube. Again, it's 2 cubed. So let's go ahead and simplify. We'll have 3 times the cube root of 8 times the cube root of 3 minus 3 times the cube root of 27 times the cube root of 2 minus 2 times the cube root of 8 times the cube root of 2. So we look at what we can do here. We know that this would simplify, it would be 2. We know that this would simplify right here, it would be 3. And again, we know that this would simplify, it would be 2. So let's go through and crank this out. 3 times 2 would be 6. So you would have 6 times this cube root of 3. Then minus. 3 times 3 is 9 times this cube root of 2. Then minus. You'd have 2 times 2, which is 4, times the cube root of 2. Now, we don't have like radicals everywhere, but what we can do is we can combine these two because you have cube root of 2 and cube root of 2. So you'd start out by just writing 6 times the cube root of 3. Then you have negative 9 minus 4, which is negative 13 or minus 13, times that common radical, which is the cube root of 2. All right, for the next one, we have negative 2 times the cube root of 162 minus 4 times the cube root of 48 minus 4 times the cube root of 5 minus the cube root of 6. So let's take a look at 162. We would first want to factor that. So what would this factor into? Well, it's divisible by 2, so let's just start with that. If I divided this by 2, I would get 81. So 2 is prime. 81 is what? It's 9 times 9. We know 9 is what? It's 3 times 3. So we do have a perfect cube here. We have 3 times 3 times 3, which is 27, times what's left, which is 3 times 2, or 6. So let's factor this as 27 times 6. So we'll say that this equals negative 2 times the cube root of 27 times the cube root of 6. Then minus. You have your 4 out in front. Now for 48, we could factor that as 8 times 6. We already know that 8 is a perfect cube. So let's do the cube root of 8 times the cube root of 6. Then minus. You have 4 times the cube root of 5. Then minus the cube root of 6. So we know that we can simplify this guy right here. This is 3. We know we can simplify this guy right here. This is 2. So what would we get if we do that? Negative 2 times 3 would be negative 6. Then times the cube root of 6. Then you have minus. We know this is 2, so you'd have 2 times 4, that's 8. Then times the cube root of 6. Then minus 4 times the cube root of 5. Then minus the cube root of 6. Now, what can we combine? When we think about like radicals, we have the cube root of 6, the cube root of 6, and the cube root of 6. So I'm just looking at what's multiplying in front. So negative 6, negative 8, and then this is understood to be negative 1, right? So it's just like if I had a negative x, this is understood to be a negative 1 times x. Same thing here. If I have a negative out in front, it's like having a negative 1 multiplying that. So I would have negative 6 minus 8, that's negative 14, then minus another 1, that's negative 15, times this cube root of 6. Then we would have minus 4 times the cube root of 5. And then these are not like radicals, so we can't simplify this any further. All right, so now we have negative 2 times the cube root of 32 minus the cube root of 108 plus 2 times the cube root of 256 plus 4 times the cube root of 4. All right, so we think about 32. We know that there's a perfect cube there. 32 is 8 times 4. Right, again, 8 is a perfect cube. So we put negative 2 times the cube root of 8 times the cube root of 4. Then minus. For the cube root of 108, we don't think about 108 that often, so let's factor that guy. So 1 plus 0 plus 8 is 9. So we know this number is divisible by 9, and it's also divisible by 3. So if we went ahead and divided it by 9, we could do 9 times 12. Then we could see that 9 is 3 times 3, and 12 is what? It's 4 times 3. And you could stop there because you know you basically have 27 times 4. 27 is a perfect cube, so we could say we have minus the cube root of 27 times the cube root of 4. Then plus, we'll have 2 times the cube root of, for 256, we don't really need to factor it. At this point, you should know it's 2 to the 8th power. So if you're thinking about a perfect cube, you want an exponent that would be divisible by 3, okay? So 8 wouldn't be, so you start going down. 7 wouldn't be, 6 would be. So you could break this up into 2 to the 6th power times 2 squared, right? 2 to the 6th power is 64. So you could put the cube root of 64 times the cube root of 2 squared, which is 4. Let's erase this. Then plus, you'd have 4 times the cube root of 4. Nothing I could really do with that. All right, so now we look at what we can simplify. So this guy right here is going to be 2. So negative 2 times 2 is negative 4. And then times what's left, which is the cube root of 4. Then we can simplify this guy right here. That's going to be 3. So you'd have negative 3, so minus 3, times the cube root of 4. Then plus, this guy right here, the cube root of 64 is 4. So you'd have 2 times 4, which is 8, times the cube root of 4. Then lastly, you have plus 4 times the cube root of 4. So now we have like radicals everywhere. So I'm just going to go through and see what we can combine. We have negative 4 here and positive 4 here. So essentially this would cancel with this, right? Those would become 0. All I'm really left with is negative 3 plus 8, which is 5, times this common radical, which is the cube root of 4.